Okay, so now that we have our salts for the hydrogen atoms, what do we do with those? So what we're going to do is we now have to think about the beryllium, okay? And so the first thing we're going to do is we're going to define the coordinate axis for the molecule. And so this is a linear molecule, and what we're going to do is we're going to say if we have an axis that goes down that connects with the nuclei of all three of these atoms, and we're going to label that our z-axis, okay? And so if you're familiar with symmetry, that'd be the highest symmetry rotational axis. We're going to define as our z-axis, okay? And so remember, we have our basis set for our two hydrogen atoms, right? We define them as a 1s orbital for HA, and then a 1s orbital for HB, right? Now the beryllium, right, we have an electron configuration for beryllium as 1s2, 2s2, but the p orbitals are close enough in energy to the s orbitals that we should consider them as well. So we're going to, for our basis set for the beryllium atom, then, is going to include 1s, 2s, and then the 2px, 2py, and the 2pc. Okay? And actually, we're going to simplify things a little bit here, and we're not going to consider the 1s, so we're going to keep this out of our basis set. Okay? All right, so what we end up with then is we're going to consider, right, what we have to do is we have to consider how these would be able to overlap constructively and destructively from between the salx and the atomic orbitals for beryllium, okay? And so we know for the atomic orbital for beryllium, right, it's going to have lowest energy 1 is going to be your 2s, right? And then we're going to have our 2pz. We have our 2py. And we have our 2px. Right. And then there are phases associated with these lobes. Yeah, there we go. Okay. And then the question is, which of these orbitals, the beryllium atomic orbitals, has the correct symmetry to interact with the salx, okay? And so let's start with the 1sHA plus 1sHB, okay? So the way we've written it, right, these, the two hydrogen atoms, the 1s orbitals of the hydrogen atoms, both have the same phase. And so in order for to be bonding overlap with an atomic orbital in beryllium, that beryllium has to have appropriate symmetry, okay? And so if we look at our four different choices here from our basis set, right, what we see is that none of the 2p orbitals would be able to overlap with this. These are oriented in the wrong direction, in the wrong axes. pz could orient in this axis, but then you'd have one where you'd have constructive interference on the other side of destructive interference. So that doesn't work. So the only option we have here that would allow for overlap between both of these orbitals, but between this both atomic orbitals within the salx, is the 2s orbital. And so, right, if we take this 1sHA plus 1s HA plus 1sHB plus the 2s of beryllium, right? What we end up with is, these are our nuclei. What we end up with is an MO, right, with overlapping electron density between all three nuclei, okay? And so this is the resultant bonding. And so this is a sigma bonding symmetry. I'm going to remove this here. As we've seen before, okay? That exhibits some sigma bonding symmetry there, okay? And so we have a corresponding antibonding orbital for that, okay? I'll erase here. So the corresponding antibonding orbital, okay, would be, for instance, if we take this SALC, and then we had the 2s orbital of the beryllium, but in the opposite phase of what we have for the SALC, right? And so what we would get is an antibonding orbital like this. So sigma antibonding. Okay, so now let's look at the second SALC, okay, because it hasn't been used for, it hasn't been combined with beryllium atomic orbital yet. So if you look at this, right, the only symmetry that would match is from the 2pz here. The px and the py wouldn't overlap at all. And so what we find is that the px and the py orbitals actually don't have a SALC, okay? And that's okay, and we'll talk about that in the next video about what that means, okay? And so if we think about overlapping the 2pz orbital with the beryllium with the SALC 1sHa minus 1sHb, what we get is, so that'll be 1sHa minus 1sHb plus 2pz. Okay, what we end up with is, this is our beryllium, hydrogen, hydrogen, right? What we're going to end up with is something that almost looks like a p orbital itself, right? It has a node right at the center. And again, we have electron density between each pair of nuclei, between beryllium and hydrogen A and between beryllium and hydrogen B. So this is a bonding orbital. And so we're going to call this A. And we have rotational symmetry through an internuclear axis. So this is also a sigma bonding orbital. Okay? And then, of course, we have the corresponding antibonding orbital for this. Okay? And so that's if we instead align the p orbital of beryllium to be out of phase with respect to the lobes or to the 1s orbitals, atomic orbitals that are in our SALC. And so we would have this. With our nucleus here. All right, and again, there's rotational symmetry through here, but it's anti-bonding. So we have a sigma antibonding molecular orbital derived from this, okay? And then in the next video, we'll show what the MO diagram looks like after considering these, okay?